Now let's look at another problem, okay? A fixed charge example.
That's a good plan. I like that plan.
This is also a very classical example of integer programming. When in a production, for example, there is a fixed cost associated with the production process. So you want to decide about how many of different types of product to manufacture. But the point is, if you decide to manufacture product 1, there is some fixed cost. For example, you have to set up the manufacturing line. Okay? It doesn't matter if your production is 1 unit or 10 units. Okay? Once you decide to produce anything, you have to incur that cost. Okay, this concept is known as a fixed cost or fixed charge, and here we are looking at an example of this type. A rice distribution company, actually a distribution company, I have chosen to put rice in here because we want to focus on the fixed cost part, not introducing integer variables because they naturally must be integer. Okay, so you will see that we will have to have variables to represent the amount of rice that we ship to different destinations, and those variables can be continuous variables. Okay, so the focus here is to use integer variables to model this fixed cost part. A rice distribution company is in the process of developing a more efficient distribution system and planning new facilities. The company is serving the demand in Boston, Los Angeles, and Houston, and currently it has one depot in St. Louis. But because of the increasing demand, they are thinking about expanding their business, so they are considering 4 additional depots in Detroit, Tulsa, Denver, and Phoenix. And obviously the company is looking for a new distribution plan. So they are saying that we are willing to rent new places, new depots in different cities because we want to have more customers. We want to distribute, we want to expand our business. Now, our problem is that we don't know which we don't know, then if we do so, we don't know what should be our new distribution plan. So we want to have a distribution plan with minimum cost. Okay, here is the information that we have in particular. So as I said, we know that we will be shipping rice to Boston, Los Angeles, and Houston. The potential depots are in Detroit, Tulsa, Denver, Phoenix, and St. Louis. We currently have a depot in St. Louis. This part of the table shows the shipping cost, dollars per ton of rice. So this, for example, says the cost of shipping 1 ton of rice from St. Louis to Houston will be $3, and so on. Okay, so this is the unit shipping cost. This part tells us about the demand that the company tries to satisfy. So the Boston needs 30,000 tons of rice, and so on. We also have the information about the capacity of the depots. The current capacity of the company is this, the St. Louis. But if they decide to rent the depot in Detroit, it will add a 10,000 capacity, a 10,000 tons to its capacity. Okay, so this is the capacity of every depot that we are considering. And the most important part is this part, which tells us information about the fixed costs. Okay, obviously, if in our expansion plan we, for example, decide to rent the depot in Tulsa, then we will have to rent the place for this much money. And it doesn't matter if we use that depot to ship 10 tons of rice or 10,000 tons of rice, okay? So as soon as you decide that you want to have a depot in Tulsa, you have to pay this much money. This cost is fixed and it is not dependent on your production. It's not dependent on your production, on your operation level at that facility, okay? So in order to make the formulation simple, let me introduce some parameters. So for the demand, instead of writing down explicitly these values, I will represent them by dj. So let's say I represents the set of my candidate sites. So when I say I mean the set of Detroit, Tulsa, Denver, Phoenix, and St. Louis. And let me use J to represent the destinations: Boston, LA, and Houston. Okay, so this will be the demand of J, where J is either Boston or LA or Houston. Let me use BI to represent the capacity of my candidate sites. Okay, let me use F of I for a fixed cost of my candidates. Okay, and for this part here, the unit shipping cost, let me use CIJ, the unit cost of shipping from depot I to destination J. Very naturally, the minimum set of variables that we have to define are of this form. So Xij, this is the minimum number of variables that I need to set a distribution plan. So technically, I should know how much rice to send from depot I to destination J. So I define Xij to be tons of rice shipped from depot I to destination J. Okay, then obviously I can easily set my objective function, initiate my objective function, I in I, J in J, Cij, Xij. This is the shipping cost, the shipping portion of the cost, okay, the cost of shipping. I have not included the fixed cost yet, okay. Now obviously, in order to do that, I need to introduce new variables, okay, because it is a fixed cost, it doesn't depend on the operation. So what I mean is that you cannot have something like f of I xij. This makes no sense because the contribution of this term will be dependent on the value of xij. Okay, so now our job is to figure out how to incorporate the fixed part. So let me introduce a new set of variables. Let me see if I can okay, I write it here. So I introduce a new set of variable, call it yi. It's a binary variable, and it takes a value 1 if depot I is rented, okay, otherwise. Now, using these variables, it is easy to cast the fixed cost, right? So it will be I in I, f of I, y. This part essentially means that if you rent a depot I, then you will have to pay the corresponding rent, right? Note that now we have to link these values to these values, okay? Because there is a logical relation between renting a place and the amount that, and the operational level that you will have at that place, okay? So what I'm saying is that the most crucial part is not defining the integer variables, but it is linking the integer variables to the continuous variables that I'm going to show you next. Okay, I will need more space, so let me go to the next page. I will write the formulation again. Just remember the parameters that I used. Okay. So as I said, we will have a set of continuous variables, also a set of binary variables which represent our decision about renting a place in city I or not renting it. And also, in order to make a formulation more compact, I'm using this set of parameters. Okay, let me go on. I already, based on these variables, I've already formulated my objective. Let me write it down again. So I want to minimize I, j in j, unit shipping cost, xij, plus the fixed cost portion for every potential candidate. If I decide to rent that place, then I will have to pay fi, right? Subject to, what are my constraints? Of course, I will have to satisfy the demand for Boston, Houston, and Los Angeles. So you are familiar with this part. So summation over i's xij must be greater than the demand of city j for every j in the set capital J. So this means for Houston, Boston, and Los Angeles. The other thing is that I cannot operate more than the capacity of my depot. So the summation over j's xij must be less than the capacity of depot I for every I set I. And I also know that these variables must be non-negative for every I in I, for every j in j. And the other variables that I defined are binary variables, right? Because they are supposed to tell me if I need to rent a place in city I or not. Okay. So I said the most important part, which is linking xij variables to yi variables, is left yet. Now let's think about the relationship. Okay, the point is, if I decide to rent a place, I have to pay its rent. Okay, and I will have to rent a place only if I decide to use it. Okay, and by using it, I mean if I decide to send something from that depot to a destination, right? So if I, in my final plan, in my optimal plan, the value of some variable xij is greater than 0, think about it. If the value of some variable xij is greater than 0, suppose that I is Tulsa, j is LA, okay? If in my optimal plan there is a value greater than 0 for xij, which represent shipping from Tulsa to LA, then I will have to rent a place in Tulsa, right? So if this is greater than 0, then I must have yi equal to 1. So I is Tulsa. Right? So think about it again. We know that xij's are non-negative. Okay, so if xij is 0, I don't care. But if xij, okay, is greater than 0, then the corresponding y variable must be 1. Which simply means that if I plan to send even 1 ton of rice from Tulsa to LA, then I have to rent a place in Tulsa, okay? And in order to, we just need to cast this relation in a mathematical form, okay? Now look at this. What I said mathematically means I want xij to be less than some big number times yi, okay? For every I in I, for every j in j. Now, look what happens. If xij is 0, okay, I will have 0 here. Then yi can be either 0 or 1. In both cases, it is satisfied. Okay? But if xij is anything greater than 0, okay, so it is, for example, suppose that it is epsilon, a very tiny value, then epsilon will not be less than n times 0. Okay? So in this case, y must be 1. Because the only way to satisfy this constraint is that you have 1 in here, so the product becomes a big number and epsilon is less than or equal that big number. Okay? So this condition here enforces that if I have a positive value, a non-zero value for xij, then the corresponding value of the y variable must be 1, and this is exactly what I wanted. Well, I wrote it as a big M, a big positive number, but when you actually try to solve this, you will need a value for M. Okay, so another question is, so what I'm saying is that this is correct, but it is not actually what we need to solve the problem. We should also say something about the value of M, okay, because M is supposed to be a number when we plug this into a computer to solve it. Okay, so big the big M, this M here, should be big enough but not very big. Now let's see if we can come up with a lower bound for M. Okay, remember, I want to force y1 to be 1 if xij, I want to force yi to be 1 if xij is greater than 0. Okay, so, and if that is the case, my constraint will be this, right? If y is 1. And remember, if this is the case, I don't want my constraint to impose any additional non-necessary, non-realistic constraint to my formulation, right? I simply want to say if xij is greater than 0, make sure that yi is 1. Okay, but if this M is small, it might affect my formulation. So I want to make sure that the value that xij can get, the maximum value that xij can get, is not affected by the choice of M. Now if I, instead of big M, I choose it to be the capacity of depot I, everything is fine. Why? Because I know that xij will never be more than the capacity of depot I. So in this case, when I force yi to be 1, this constraint will be of the form xij less than or equal bi, or simply saying that you cannot ship from depot I to destination j more than the capacity of that depot, okay, which is absolutely valid. Okay, so there was 2 points in here. The first one was how to use binary variables, okay, to cast the fixed cost. Also how to relate those binary variables to your continuous variables. And an additional point was how to come up with an actual value for the big M here. So this will conclude the fixed cost problem. Once again, I want you to focus on 3 things. 1, introducing binary variables to cast fixed cost. 2, linking those binary variables to the let's say original continuous variables. In here it was xij. And 3, determining a lower bound on the value of big M. So these are 3 points that you should consider when you formulate a fixed cost problem.
Say what you want. I think it's all beautiful.